In this video, we would like to talk about graph traversal. Graph we already have idea, which is one advanced data structure managing objects and object relationship. Give a complex, let's say give a big graph, right? They have 1,000 nodes, 1,000 objects, and the relationship, it is very intensive. And give 1,000 big network, and we would like you quickly find out, quickly scan, or quickly visit, find and visit, or discover every vertex information. And also the most important is, since it's time for time efficiency, we would like to make sure each node, each object, you just visit for once. Without a specific order, it's difficult task, right? So when we use a certain graph algorithm, we could ensure that each vertex of the graph is visited exactly once. The order in which the vertices are visited are very important and may depend on the algorithm or question that you are solving. So it means today we will give two graph traversal strategy. In that case, it specifies the order such that we can walk through the whole graph and visit every object just for once. During the traversal, it's important that we track which vertices have been visited. The most common way of tracking vertices is to mark them. So we will see here, we will use specific, we use column to say this vertex, this object has been visited, and all the related information has visited. So this is all doesn't visited at all. So it means at least we have 3 status. We need to use a specific thing to mark these 3 status. Namely, given a graph G equal to VE and a source node S in V with vertex, E is the edges corresponding to vertex relationship. Start with S and follow its node relationship. To walk through a graph, let's walk through for the specific order. Discover all other vertices in a graph. And today we will check 2 strategies, BFS and DFS. First, let's check BFS. BFS is brightest first search. What corresponding to that? With all this traversal problem, give a graph, just like here, give this graph, and give the starting point. Let's say A is the starting point. We would like to discover all the nodes for once. And the brightest first search strategy allow exploring the edges of G to discover every vertex that is reachable from S. And brightest first search is named because it expands the frontier between discovered and undiscovered vertices uniformly across the brightest of the frontier. That is, algorithm discovers all the vertices at a distance k from S before discovering any vertex at a distance k plus 1, the brightest first. For example, you have A, starting from A, and we check all vertex which connect with this A. We check this A and all the undiscovered related nodes of A, and we discover all these directly connected nodes with A first. After that, we want to explore the later vertices connect with each specific child node of A. So it's brightest first. When we explore A's children, we make sure we explored every children before we go to the next hops, right? If this is load, and through the one connection is one hop, in that case you have A, F, C, B. A is connected with B, C, F. It corresponding to one hop from A, we can reach to B, C, F. And through B, we can access through one hop, access C, D. And such that, right, from A to C, A to B, B to D. And such that from A to D, we need to have two hops. This brightest first search corresponding to we starting from the source node, and we check what is the one hop based neighborhoods. One step neighborhood first, then we check two step neighborhoods. And every time we check one step neighborhood, we check all the neighbors in that step, step one, right? And then after we check all the neighborhood in the step two, in the hops two, in the two connections. This is we talk about the brightest first search. And later we will check how to design the algorithm. And this have wide usage. It can be used to compute the distance from the source node S to each reachable vertex to see how many steps you need to reach from S, starting from S, visit to another node. It can also be used to produce a brightest first tree with root S that contains all reachable vertices. For any vertex V reachable from S, the simple path in the brightest first tree from S to V corresponding to a shortest path from S to V in G, that is a path containing the smallest number of edges. Okay, so this is applications. And now let's just see what it is how can we design for that, right? Okay, let's use computational way to formulate this problem. Give graph G equal to a tuple of V and E, either directed or undirected, and the source vertex S belong to vertex connection. And we would like to identify a brightest first tree starting from S, and also corresponding to we want to find all reachable vertex which has shortest path from S to either reachable vertex. And such that to discuss our algorithm, let's use some symbol. Let's define, since we care about the shortest distance from the source node S to each reachable node through the one-step neighborhood, two-step neighborhood, or more step neighborhood, right? And now, since the graph allows cycles, and the question is, can it stop somewhere? And in such way, if all the vertex has been visited, and also just visit for once. You don't repeat to retrieve the information of that vertex, right? So we needed to have the array, corresponding distance array, from S to each reachable node. And how can you make sure each reachable node is reachable? In the beginning, we don't know. So this reason, we have array, distance array, which includes n elements. Each element corresponding to n minus 1 elements. Each element corresponding to all other vertex except starting node. Okay, in the beginning we set to be infinity, because we're not sure is it reachable from S to that vortex or not, right? So the index of each element corresponding to the vortex in the graph. And we also use pi array. Pi array, we want to since it's the form brightest first tree or propagation tree. In that case, we also need to maintain this parent-child relationship, and such that we use this pi and pi v equal to u, such that uv is last edge on shortest path. So it means u is v's predecessor, and also corresponding to v, u is v's parent in this brightest first tree or propagation tree. And the output also corresponding will build the brightest first tree with root S that contains all the reachable vertices. Okay. And then the definition, let's say here we show the definition. Path between the vertices u to v is a sequence of vertices v1, v2 through vk such that u equal to v1 and v equal to vk and vi plus 1 belong to H for all I it is larger than or equal to 1, smaller than or equal to k minus 1. That makes sense, right? This is the path. It's a sequence of vertices v1, v2 through vk. And you can see here we talk about the simple path, and no vertex is repeated. Length of the path. Number of edges in the path. Path is simple if no vertex is repeated. Yeah, so this reason, this path here, we do not separate it's simple, not simple, right? So if we see vi equal to v, some specific index, in that case it's not simple. Here, since we consider is a shortest path, and corresponding to the length of the path is the shortest. In that case, definitely we want to find a simple path. Expands the frontier between discovered and undiscovered vertices uniformly across the brightest of the frontier. This corresponding to what we have, the brightest first search, the brightest first, and each element in the same step I neighborhood should be uniformly accessed. A vertex is discovered the first time is encountered during the search. A vertex is finished if all the vertices adjacent to it have been discovered. Right? So we say we need to maintain 3 status: discovered, finished, or not visit, right? Colors the vertices to keep track of progress. White, undiscovered; green, gray, discovered but not finished; black, finish. In the beginning, every node has a color white. Colors are required only to reason about the algorithm, can be implemented without colors. So in the beginning, for this BFS, brightest first search, we define 3 arrays: color array, distance array, and previous vertex array corresponding to parent array in the propagation tree. And in the beginning, we set each color to be white, the color for each node to be white, distance for each node is infinity, and the parent nodes, or for each node, it is long. And then, since we're starting from S, this BFS also corresponding to, we propagate. Let's write it down here. So the BFS, we want to find the brightest first search tree. And also corresponding to propagation tree. Given a graph, G, VE, and source S, we would like to check how far the source we want to check the we want to find all the reachable vertices. For example, step 1, label hood. Step 2, neighborhood. Step 3, neighborhood. And they could have more, right? Could have more. But we have to find out what it is the first this source can reach to. Neighborhood, right? This also corresponding to messaging passing. Or rumor. Passing. Right? Let's use the social network as an example. And A has a friendship. As you see, since the friendship is no direction, right? And D let's say their friendship, right? Their friendship. Let's say this is exactly everybody connect with each other. So the message passing corresponding to starting, let's say S, it is A. And the message pass from A to B and C, right? Let's use another color to represent this is messaging passing, right? And after that, propagate messaging from B and C to the adjacent vertices. And here, since A was connected with D, and we also have another one, we have D here, right? So in that case, then you have to trying to propagate the message. And then in that case, since If we have more, we have E here, right? And or F here, right? So in that case, it is, we could have E and F adding here. And this D, you already have, right? This one you already have. This is step 1, neighborhood. And this is step 2, let's write it down. The step 1, the second step. And this is one step, and the second step, and this is another second step. And in this case, since we have to, since we need uniformly visit the undiscovered adjacent nodes before we go to the next level. And in such case, it is, we see that in the graph, each node, we have a linked relationship with another one. You can access that. And once from A, you access B, and you want to make sure when you access C, you still have B saved somewhere. Before later, you have to access E, right? The order of this access, if this is 1, you have 2 here. This is the, let's use another color to represent the order. The order, of course, is 1, right? Let's use O to represent. Okay, let's write down here, order 2, right? And this is the order 3, and this is the order, okay, this one, right? Order 4, and order 5, and order 6, right? So it followed this order. And such that we already talked about, we need to have a distance, let's use distance array, D array, and we have the parent relationship array. We also have the corner array, right? This is represent is accessed or not accessed. And keep in mind here, when we access this one, we access adjacent vertices. And before you finish this one, you have to keep this one somewhere, because you need to make sure and when you access this one, you have to remember this B, or you have to remember all the children of this B if it is not no. Or is no, you visit this B, or you visit all the children, or save all the children of this B. We see here, once you finish this checklist, when you visit this B, and you need to check all. When you check A, you need to save the information of B, C, D, right? And you need to make sure B, C, D, they should be uniformly handled. And in that case, we want to save this one to somewhere. And also based on who comes first will be served first. And it gives us intuition we need to use queue structure. It's useful, right? Queue structure to use for this uniformly accessed next step neighborhood. We have to save it somewhere. And who come here, who can list the labels and save this labels information if that is corner is unvisited. And then after that it is once all the adjacent vertices has been accessed, then we can say this be finished the task, right? So this is it. We need to use queue structure to access being discovered vertices. Once this vertex is finished, then in that case you can release from the queue. Okay, so once we have this discussion, it will make us very easy to understand this pseudocode. This part we already discussed. This part we already discussed. This is for initialization. And this also makes sense. We initialize the distance to be infinity, right? From S, let's see here. This is A to B. Doesn't matter it is infinity or doesn't matter it's directed or undirected. For example, right? This is also the S. You access from here. And you want to find the propagation tree. Since we need to find it in the beginning, you want to find all the reachable vertices. And so the distance is infinity, the parent is long, and the color is white in the beginning because it's not a discovery. And then after that, you see this is you are discovering this one, and the distance is 0, and the parent load is long, and the Q is assigned to be Q is assigned to be empty, and you have S put in the Q, right? So let's see this Q structure. And Q structure also corresponding to the elements, the loads, the vortex you are discovering. And once you put in the Q, discovering that, right? It means discover. If there is put in the Q corresponding to discover the vortex. And once you put in the Q, discover that this is in Q. If it's in Q, we discover that. If we DQ, corresponding to finish. Finish vortex, right? So this is the basic idea. So even I do not need to put the S here. This corresponding to DQ, in Q. Okay, so now you have S put here. We will try to discover this all the relationship, connected with this S, right? And then after that, we DQ because we are sure, the net elements. We want to check that for each V in adjacent U. Since we retrieve it as the U, right? This is U is what you retrieved. U corresponding to what you retrieved. What is this one? U is S, and from the S, corresponding to what you have the A here, right? And then for each adjacent vortex of this A, you put each is one. You change the corner. As you see, we also have corner, right? You have corner array. So we have a corner array. And we have, except the corner, we have distance array. And we have a parent array. Right? Let's use this one example to check that. And then, so let's say we use this is number index 1, 2, 3, 4, right? the index 1, 2, 3, 4 corresponding to A, B, C, D. And then since A connect with B and C, and so for each step 1 neighborhood, for each label, step 1 label, and we assign this one to be, if this is white, then you want to change to be gray. Since this we check for, in the beginning this is a G and this is a 0 and this is the none, and then you check for B and C. B and C here is neighborhood, have G, and the corners, the distance, you have based on this one plus one step, and you have parent, put what is A, right? A should be here. And then you check also C is adjacent, so you have G here is the step 1, and also this A is a parent. And then after you do each one, you need to put B and C in the queue. And then go back to here. You DQ. This one got removed, right? Because you DQ corresponding to, you're trying to finish this vertex. And once you check for BQ, you go to here, B, when you wait the B, you check the adjacent nodes, which have D, and also C. Since C, the color of C is gray, so you cannot visit that because this is widely been discovering, right? And such that only D, you want to check that, and the color need to change to be G, and this is the second step label, and the parents corresponding to what you have the B as the parent, right? And then after that, after you finish this one, we have to change the color to be black. Same thing here. Change this one, right? The previous step, when you finish let's use another color. This is a B, this is a B, right? It's corresponding to you finish it. This is you finish it. These two, you already finish it. Exercise. And then such that you continue, and also here, once you finish it, you put the new access D to here in the queue. And after that, you go back to here and get a DQ. This got to move out. And then once you got to move out, you check all the adjacent nodes, right? In this case, you have A and B, but you know they both do have color, right? In that case, you finish it. You just finish it. This C with no any change on this 3 array, and then after that, you continue check and DQD, and then in the D, same thing here, right? So once you finish C, you change this one, change the color to be B. Let's use different color. Change to be B, right? And after you finish this, DQD and finish that, change it to be B. So in the end of this algorithm, the color array, every element is filled in with B, and the parent nodes here, which corresponding to, which lists the precedence of each nodes, who is the parent in this propagation tree. And the distance tells how many steps for this label from the S to that vertex. I think this algorithm is very clear. And now let's give an example to see we have this graph, and this is an adjacent list to show this relationship. And we're trying to starting from A. A is the source node. So A is in the queue, and we put B in the queue. We trying to discover B, and we see the first step. The step 1 neighborhood, we have to explore that uniformly. So we have connected BCF. This is 3. We have to change the kind of this one and also put in the queue, right? And then after that, after you finish this A, move out from the queue. And then after that, you retrieve from the queue, retrieve B and find the unexplored, undiscovered, the next hop, the next neighborhood. And D put in the queue, and after the B finish, then you check for C, and then since the C nodes is connected with that, and then you finish C, change the color, and check for F. And after you check F, F have A and C, both is not white. So this reason you finish the F and finish the D. And then you can see here, after that you can see this is what you have the propagation tree, right? If we go back, and you will see this is the first step, first hop. And first hop reach to FCB. Second hop, let's see, 1, and this 2. Second hop, you reach to D. And this G and E, if you start from A, will never be reached, right? And such that, and sometimes if the interview question, they give to you to say explore all the nodes by using BFS. We have to make sure if they have meet a lot of white nodes, if you find the color array, they have some element still keep as white. In that case, you have to randomly choose one and to explore until all the elements in the color array, it is black. Okay. And this BFS, you can see this is the what we show the original graph. This is what we have the propagation tree, right? And also to show you the distance between the source node to the first level neighborhood and the second level neighborhood, and this is propagation tree. And in this case, we found out the propagation trees. And this algorithm can also help for undirected graph. The message, the way to work on that is the same. Okay, I think this is the BFS. Let's